In this video, we're going to look at implicit differentiation. Now, we've been deriving functions when they're explicitly defined. So something basic like this, y is equal to x squared. And so we take the derivative of the y, dy dx, and we get 2x. We started with a y value that was explicitly defined, meaning if I plug in any value of x, I'm only going to get one resultant y value. The same thing is true for its slope then, because we only have that one position. So for instance, if I think about the x squared function, we know it looks like this. If I say, hey, x is equal to 1, we know exactly where that is, and we know what its slope is going to be. Or if I look at x is equal to 2, I know exactly what its slope is going to be. But differentiation shouldn't just work with things that are functions. It also has to work with things that aren't functions. So what if we have something like a circle or an ellipse, where if I have that one value of x, it doesn't correspond to just one value of y. So that brings us to our implicit differentiation. So let's say we had the function y squared is equal to x. This isn't explicitly defined in terms of y, it's not a function. I have two y values for every one x value, and so I can't just define it in terms of those x values. So the process is going to be very, very similar, just with a slightly added twist. We think about what we did up here. When we started with that y, we said, well, we're going to take the derivative of y with respect to x. And the derivative of just one y was just 1, because if we just had x, what's the derivative of x? It's just 1. There's just one of that variable, and so the derivative of y is dy dx. But here, now when we go to take this derivative of the y, the derivative of y squared, using our same power rules as before, the derivative of y squared is 2y. But what we've just done is we've taken the derivative of y with respect to x. So I'm still writing that dy dx there, it's just now there's something attached to it where we didn't before. It's the exact same operation. We just never really thought about what we're doing with this y. It just disappeared. Why did it disappear? Well, the derivative of just a y, derivative of just an x, is 1. Once that y is something a little bit more complex, then we have to track it. We've got to pay attention to what its derivative is. So let me finish out this problem. We wanted to find, I never wrote out what we're trying to do, but we're trying to find dy dx. So we see that dy dx has appeared, same way as it did before, it's just now there's something else with it. So I do want to isolate that dy dx though. We see that dy dx is 1 over 2y. And that's our derivative. A little bit different than before. Notice we don't even have any x's involved, and if we think about why that would be, well, that relies on our knowledge of the shape. X equals y squared is a parabola that opens left and right. And so if we're going to talk about the slope at any point along this curve, it doesn't matter what the x is because it matters on what the y is. If I say, hey, find the slope when x is equal to 1, I'd say, well, great. Do you mean this point right here? Or do you mean this point down here? I don't know which one. Versus if you just said, hey, find the y value when, find the slope value when y is equal to 1, I know exactly that point. Or if I want to know the slope value when y is negative 1, I know I'm looking at exactly that point. So no longer does the function strictly depend on x, or it might not even depend on x, it might depend on the y. We should always still find that we have that 1 dy dx value because at any point along these curves, it doesn't matter what the curve looks like, however crazy it gets, there is only one slope value for any point along these shapes. Now it might be that we have to have a y and an x, because if I look at this crazy shape here, this point here does not have a unique x value, and it also does not have a unique y value. So we do need to be aware that sometimes these things are going to rely on both the x's and the y's. Let's do another one. Let's find dy dx for 5x squared plus 3y squared equals 4xy. So now I have y scattered on both sides, and there's no way for me to solve for y because this isn't a function of y. It's some sort of conic section with a rotation. So we want to try to get to that dy dx, which means we're going to have to take a derivative. Take the derivative of 5x squared gives us 10x. Derivative of 3y squared is 6y dy dx. And then we get to this side, in 4xy, well, we have two variables multiplied by one another. So what do we have to do when things are multiplied by one another? We have to use our product rule. So I'm going to take the first term, and I'm going to leave it the same for right now. I'm going to take the y, and I'm going to take its derivative, dy dx. Kind of like with the early ones, we did before today, if we just have that y, it just becomes a dy dx. But then, because we are using the product rule, I have to also take the derivative of 4x, which is 4. Now I leave the y. Now my goal was to find dy dx, and so that means I'm going to need to get this dy dx piece by itself. So anything that's a dy dx, I'm going to move to one side. Anything that's not a dy dx, I'm going to move to the other. Doesn't matter which way you move. I prefer usually to move my dy dx's to the left-hand side, just kind of habit, and it looks nicer. But sometimes I switch that, and it really doesn't matter which way you move as long as we are keeping track of our signs. So I subtract my 10x to the right-hand side. I subtract the 4x dy dx to the left-hand side. And now because I have the dy dx's on one side, I can factor it off. So I have 6y minus 4x equals 4y minus 10x. Then finally divide off what is not dy dx. And so there would be our derivative. Now I've been using the dy dx's throughout so far, and that's fine. We can always do that. But remember, a lot of times, just for shorthand, we use dy dx where we represent that as just a y prime. It's a little bit of a shorthand. We can do that here, and I think it really saves us a little bit of time to do that here. Where this is going to fall down, or where we can't just use that y prime, is when we have multiple variables, or if we're looking at multiple parameters within a problem, we're tracking things differently. So as long as we only have those two variables and we're looking at the derivative of one with respect to the other, very common to use that y prime. So I'm going to just switch to that to save myself a little bit of time. So let's take the equation sine y, to be sine y minus cosine x plus y to the 4 power equals 3. So our goal is to find the y prime or the dy dx being the same thing. So I see the sine y. Well, this requires a chain rule now because that y is inside the trig function of sine. And I know the derivative of sine is cosine y. But then because I just took the derivative of y, or once we get to the inside of that function, we're taking the derivative of y, and the derivative of y is y prime. So I'm going to write down that times y prime. Derivative of cosine is a negative sign, so that's going to switch that term back to positive. Sine x, and the derivative of the inner function there is just 1. Y to the 4th, the derivative of that is 4y cubed times the y prime. And then on the right-hand side, the derivative of 3 is just 0. So that chain rule, see, we had trig functions on both of these, and here we really didn't have to worry about the chain rule. Derivative of cosine, we just got the negative sign, and we're done because the derivative of x is just 1. When we take that derivative of y, we've got to remember the derivative of y is that dy dx, or the y prime. Now I'm going to work to get the y primes all on one side. And once I do, I can factor off that y prime. I have cosine y plus 4y cubed equals a negative sine x. And then I'm going to divide it off to get the y all by itself. Y prime equals negative sine x over cosine y plus 4y cubed. And we could find whatever slope we wanted to. If we were looking for the slope at the point 1, 2, we could plug in the 1 for x, the 2 for y, and we can solve that. But I'm just concentrating getting to the derivative at this point. We found higher order derivatives before. We can do that with our implicit differentiation too. So let's find y double prime of e to the y plus xy equals x squared. Again, something that I can't explicitly define in terms of y, so I'm going to take the derivative as I see it. I'm not going to bother rearranging anything. Derivative of e to the y, well, the derivative of e is always e is itself, but then because we took the derivative of y, we have to track that y prime. Now I get to a product. The x is going to stay the same. The derivative of y is y prime. And then we take the derivative of x, which is just 1, times the second term, which is the y, it stays the same, equals 2x. So before we go on to take a second derivative, I need to isolate the y prime. I want to see what that first derivative looks like. That's going to make it much easier to see what the second derivative looks like. So I'm going to get the y primes to one side, meaning I need to take the y, the third term there, and subtract it over to the right-hand side. So we'll have 2x minus y. And now I'm going to factor the y prime off. And now I can divide, so y prime is equal to 2x minus y over e to the y plus x. So there's our first step, but we were asked for the second derivative. So now I've got to take the derivative of this thing. Well, here's where it's nice to solve for the y prime, because we're always solving for that y prime first. We take the derivative of y prime, that right away gives us a double prime. We don't really have to worry about bearing that y prime in there even further. Now, when we take the derivative of the y's on the other side, we're going to see some more y primes pop up. But for now, to get to that second derivative, we just take the derivative of the y prime, we get to the y double prime, and we will have to use a quotient rule on the right-hand side. So this will be a little bit messy. We know that we take the denominator and we leave it. And then we have to take the derivative of the numerator, which will be 2 minus y prime. And then we're going to subtract from that. I'm going to leave the numerator, leave the top. I take the derivative of the bottom, which will be e to the y times y prime, because we have to do the derivative of the inside. And then the derivative of x is just 1. This is all over e to the y plus x. And there we have an equation for the second derivative. Now there's one more step I'm going to add, just because if I'm looking for the derivative, the second derivative at a point, I'm not going to have that y prime initially, so we could plug in the numbers and get the y prime, but a lot of times it's just nicer to go ahead and get that done in terms of the equation. So I'm going to take my y prime and plug it in here. I know what the y primes are because we found that. So my y double prime, we have our e to the y plus x, 2 minus, and the y prime was 2x minus y over e to the y plus x minus 2x minus y e to the y times the 2x minus y over e to the y plus x. And I still have that plus 1 beside it. Actually, that looks like a y. And there's our plus 1. Close my parenthesis, plus 1. Close that parenthesis. And then this whole thing is still over the e to the y plus x. So it's gotten quite ugly, but we have it all in terms of x's and y's. If we wanted to, we could simplify by multiplying through a few things. So here those would cancel very nicely. We'd have to distribute to the 2. Here we'd still have that in the fraction, so maybe it'd be a better idea to multiply that across the whole fraction. But that gives us that second derivative, and then depending on how far we want to simplify, we can go from there. So implicit differentiation, Really no different skills, nothing different than what we've seen before, other than the fact that we've never really talked about what do we do when it's not just a y. Well, we take the derivative of that y as we would any other derivative, but we have to then make sure that we are writing that dy dx.